Hi, this is Sir Aris. Let us talk about still second order linear equations, but we'll consider cases with complex roots of the characteristic equation and repeated roots. We'll also see what this reduction of order means. Um, okay, so for the first part, we have we will still continue um, solving or discussing about the solutions of this equation. This is a second order differential equation of um, homogeneous type. So there's a zero here. A, B, C are real, the coefficients. So if we seek solutions of the form y equals E R T, R must be a root of the characteristic equation AR squared plus BR plus C equals zero. We have seen or showed this. We have shown this previously. Um, so the roots are given by the quadratic formula, and for this section, we consider the case where this b squared minus 4ac is less than 0, so that we have the square root of a negative term or an imaginary number. The complex solutions can be written as R1 equals lambda plus I mu, and R2 as lambda minus I mu, where lambda generally would be b minus b over 2a. Mu is I of the square root of the absolute value of this divided by 2a. The corresponding expressions for y are, so y1 is e to the power of r1, which is this, times t, and e to the power of r2 times t. You might be wondering what would happen if you have an imaginary number on the exponential. So we will use something called Euler's formula. Um, we will try to derive this later on, maybe as a homework or as part of the topic in after two chapters. Or if not, if we can also you'll be able to encounter this in, for example, mathematical physics one course. That's physics 122. We'll just um, accept this as it is. We will not show how uh, this identity comes about, but just believe that this is true. Okay, so we have e lambda plus I mu t. We can fact distribute t and then separate the additive uh, terms. So e lambda t e I mu t. So e I mu t is given by this expression cosine mu t plus I sine mu t. This plus minus here means that if it's plus, then you choose plus. If it's minus here, you choose minus. So for example, find the general solution of the differential equation, this differential equation, and also find the solution that satisfies the initial conditions given and draw the graph. So as the first part, um, we use the characteristic equation. So the characteristic equation is 1 plus or 1r, so I'll just write r squared, um, plus r plus 9.25, so that the roots are given by r equals minus 1, so minus b, plus and minus squared of b squared, 1 minus 4ac, 9.25. divided by 2. Okay, 4 times 9.25, that's 36 plus 1, so that's 37. So 1 minus 37, that's minus 36. Okay, or minus 1 half. Plus and minus, this is minus, square root of minus 1 is I. Okay. Square root of 36 is 6 divided by 2, that's 3. So this is 3I. Okay, so the two solutions are y1t equals e to the power of um, r, which is one of this, so minus 1 half, plus 3I times t. Oops. This is equal to e to the minus t over 2, okay, minus 1 half t, times e to the power of 3it, which would be cosine of 3t plus I sine of 3t. Okay, and y2 equals e to the power of minus 1 half minus 3it. So that's still e to the power of minus t over 2 cosine of 3t. Let me write that properly. Cosine of 3t minus, so since there's a minus here, minus I sine of 3t. Okay, so the Wronskian W given by y1, um, so it's a matrix, or the determinant of the matrix y1, y1 prime, y2, y2 prime. Okay, y1 is this, so let me use this term here. It's easier. Exponential minus 1 half plus 3i t. The derivative is minus 1 half plus 3i exponential minus 1 half plus 3i t. Here you have exponential minus 1 half minus 3i t. The derivative is minus 1 half minus 3i exponential minus 1 half minus 3i t. Okay, and then you take the determinant. Okay, so you simply multiply this to this plus 3i here and minus 3i would cancel, so you just have exponential minus 1 half t times exponential minus 1 half t, that's e to the power of minus t, okay, times minus 1 half minus 3i minus this and this again, almost similar, but you have minus 1 half plus plus 3i, this, okay, this plus um, this minus 1 half here and minus 1 half would cancel out, but this minus 3i and this positive 3i will not uh, cancel out, so you have minus 6i e to the minus t, which is not 0. Okay, so this tells us that the solution, or y, if the Wronskian is not 0, then this y1 and y2 are sets of solution, fundamental sets of solutions. So we have um, so therefore the solution y equals c1 y1 t plus c2 oops, plus c2 y2 t is a solution. Okay. Now to express the solution in terms of real valued functions, we use this theorem, which we will not prove. If you want to prove, the proof is straightforward because you just have additive terms here. So it is very easy to show that if this complex valued solution of a second order, which is differential equation, the real part and the imaginary part u and v are also solutions of the equation. So from either y1 or y2 up to negative sign, overall negative sign on v, but it doesn't matter. You have u equals e to the minus t over 2 cosine 3t, and v equals e to the minus t over 2 sine of 3t. So the Wronskian can be written as ut u prime t vt v prime t, and then you take the determinant of that matrix. Okay, ut is e to the minus t over 2 cosine 3t. The derivative is minus 1 half e to the minus t over 2 cosine 3t minus, so cosine of 3t is negative sine 3t, so minus 3 e to the minus t over 2 sine 3t. Okay, vt is e to the minus t over 2 sine of 3t minus 1 half e to the minus t over 2 sine of 3t plus 3e to the minus t over 2 cosine of 3t. Okay, all of these terms contain e to the minus t over 2. So we can factor out. So if you multiply this times this, e to the minus t over 2 times e to the minus t over 2, that's e to the minus t. All of the terms have that, so we factor out e to the minus t. Cosine 3t times this, so you have minus 1 half cosine 3t sine 3t. Cosine and this, so that's plus 3 cosine squared 3t minus this and this. So there's a minus sign, which becomes plus 1 half cosine 3t sine 3t, and then another plus again, 3 sine squared 3t. Okay, this and this cancels. Cosine squared 3t plus sine squared 3t, that's 1. So you have e minus t times 3. Again, this is not equal to 0. Okay, so we can write the solution we can write the solution as y equals c1 ut plus c2 vt, or e to the minus t over 2 c1 cosine 3t plus c2 sine of 3t. Okay, now with the initial conditions, um, y 0 equals 2 and y prime 0 equals 8. So for y 0 equals 2, you have, so let me write that here. Okay, y equals e to the minus t over 2 c1 cosine of 3t plus c2 sine of 3t. So y of at time t equals 0 becomes 1. You have c1 cosine of 0. So let me write it explicitly. Plus c2 sine of 0. Sine of 0 is 0. Okay, but this is 1. So you have that's c1. And this is equal to 2. Okay, from here. Okay, c1 therefore is equal to 2. Okay, now if you take the derivative y prime of this is function of time, equals e to the minus minus 1 half e to the minus t over 2 of c1 cosine 3t plus c2 sine of 3t plus e to the minus t over 2 of c1 are negative 3c1 sine of 3t plus 3c2 cosine of 3t. Um, Setting time to 0, so this becomes 1, so you have minus 1 half. Okay, this is also 1. c1, this if this is 0, this is 0, so you have c1. Okay, this is 0, so you have plus 3 c2, and this is equal to 8 here. Okay, c1 is 2 from here. Okay, the c1 becomes 2 plus 3c2 equals 8. 2 divided by 2, that's minus 1, so 8 here becomes 9. 9 divided by 3, c2 equals 3. Or finally, y equals e to the minus t over 2. 2 cosine 3t plus 3 sine 3t. And if you make a plot, the plot would look like this. Okay, so there's a decaying oscillation, and um, exponentially decaying due to this term here. If we consider the general case, you have, let's say, for our second order differential equation equals 0, then you have um, solutions y1 equals exponential of lambda plus I mu t, which we can write as e to the power of lambda t cosine mu t plus I sine mu t, and y2 as exponential or e to the power of y minus I mu t equals e lambda t cosine mu t minus I sine mu t. Either of the two up to a negative sign, you can have u um, equals e lambda t cosine mu t, and v e lambda t sine mu t. The Wronskian w is um, e lambda t cosine mu t, its derivative, so lambda e lambda t cosine mu t plus e lambda t, or that's 3, or mu negative sine mu t. Okay, here you have e lambda t sine mu t lambda e lambda t plus e lambda t mu cosine mu t. Take the determinant. All have lambda t, so we can factor out e to the power of 2 lambda t. Cosine is this, so that's lambda cosine mu t sine mu t plus mu cosine squared mu t minus this times this. We have lambda cosine mu t sine mu t plus, instead of minus here, um, minus mu sine squared mu t. Okay, this term and this term cancels out. If we add this two, it's just equal to, so cosine squared plus sine squared, that's 1. So you have mu e to lambda t, which is not 0. Therefore, the solution y can be written as c1 e lambda t cosine mu t plus c2 e lambda t sine mu t. Okay, so another case when, again, if you have the characteristic equation, um, a r squared plus br plus c equals 0, the roots are minus b plus minus square root of b squared minus 4ac over 2a. Now, if b squared minus 4ac equals 0, then r would be minus b over 2a. But it's not only 1, it's just 1r, but of multiplicity 2. Okay, just one value, but two roots of this same value. Okay, or our characteristic equation can be written as b r plus b over 2a times r plus b over 2a. Okay, so one solution is that y1 equals e to the power of minus b over 2at. Now the difficulty is that what is the second solution? Okay, so to solve for this, we okay, to find the or a second solution, we assume that y, the solution, can be written as vt y1t, or that vt is e to the minus b over 2at, where vt is unknown. Okay, so if you have that y, there's a tricycle or a motorcycle. Uh, okay, y prime is v prime t, y or e to the minus b over 2at minus b over 2a v t e to the minus b over 2a t. Okay, if you take the second derivative, you have v double prime t e to the minus b over 2a t plus v prime t. Take the derivative of that, b over 2a e to the minus b over 2a t. Okay, minus b over 2a v prime t e to the minus b over 2a t. Take note this and this are the same. Okay, plus this, take derivative of this, you have b squared over 4a squared vt e to the minus b over 2a t. Okay, or that y double prime is v double prime t e to the minus b over 2a t minus b over a, removing the 2, v prime t e to the minus b over 2a t plus b squared over 4a squared vt e to the minus b over 2at. So we substitute y prime, and y double prime in our differential equation. You want to see, we have a times this. So a times this, you have, take note that all of them contains e to the power of minus b over 2at. So that it would make our life easier. We'll factor out e to the minus b over 2at. Okay, so the first is this a times v double prime t. Okay, just writing this properly, you have double prime t. A times this, you have minus b v prime t. A times this, you have b squared over 4a vt. So you have y prime multiplied by b, you have b, okay, plus b v prime minus b squared over 2a vt, and finally plus c of vt. See here, e to the minus bt over 2a. This is not 0, which means that this whole thing here should be 0. Also, this and this would cancel out. So we can write a v double prime t plus, or actually minus, b squared over 4a. So this is 1/4 minus 1/2. That's negative 1/4. So you have b squared over 4a vt plus c vt equals 0. 2v, this vt's here can be factored out. So you have a v um, minus vt, b squared over 4a minus c equals 0. But this is equal to 0 because We use the special case b squared minus 4ac equals 0 that we have mentioned here. Okay, so we are left with v double prime equals 0. If we integrate this, you'll get v prime equals some constant. If you integrate that again, you have v, this dt. You have vt written as constant times t plus another constant. So that um, you have y equals c1, um, just for to keep track easily of the variables. I'll just write c1 times um, uh, a plus c2t. Okay, so that y equals vt. We have here vt y1t. So that's vt, which is c1. Oops, c1 e to the power of minus b over 2a t, um, plus c2 t e to the minus b over 2a. So y is a linear combination of y1, which is e to the minus b over 2at, and y2, which is t times e to the minus b over 2at. The Wronskian we can write as e to the minus b over 2at. Its derivative is minus b over 2a e to the minus b over 2at. And the second row is t e to the minus b over 2at. Take the derivative e to the minus b over 2at plus, actually minus t times b over 2a e to the minus b over 2at. Okay, if you multiply this, um, all of them will have e to the minus b over at. So we remove 2 because if you multiply this, for example, times this, you have b over a, negative b over at. Okay, so this times this, that's 1, minus this times this, that's t, uh, t b over 2a, then minus this times this, which is actually plus, this times this, it's t, or b over 2at. This 2 cancels out. So we are left with this term, which is still not 0. Therefore, y1 and y2 are or form a fundamental set of solutions. For example, let's consider this problem. Find the solution of the initial value problem. The characteristic equation is 1 minus, or r minus r squared minus r plus 0.25 equals 0. So you can write this as r minus 1 half times r minus 1 half. So the root is 1 half of multiplicity 2. So the general solution is y equals c1 e to the minus or positive 1 half t plus c2 t e to the 1 half t. Okay, using, if we set y or time t as 0, you have c1, this is 1, and this is 0. Okay, but from boundary, our initial condition, y0 is 2, so this is equal to 2. Okay, so if you get y prime t, take the derivative, that's simply c1 1 half e 1 half t plus c2 e 1 half t plus c2 t 1 half e 1 half t. Okay, if we set time our the variable t to 0, so this is 0, this is 1, this is 1, so you have c1 over 2 plus c2, and again y prime 0 equals, oh, I'm not sure if it's 8, 1/3. 8 is from the previous example, so you have here 1/3 equals c1 is 2 plus c2, so this is 1. So c2, okay, this tells us that c2 is equal to, so this 1 minus 1/3, that's minus 2/3. That's our c. We have c1, we have c2, so we can write y equals 2 to the power of e 1 half t minus 2/3 t e to the 1 half t. Okay. Finally, if you consider non-constant coefficients, you have pt, qt, and suppose that we know one solution. To find the second solution, we can use the result from the previous topic for um, characteristic equation with a solution of same roots. Okay, or let me return to that. So there, what we did here, or repeated roots, um, we apply to a this equation, second order homogeneous differential equation. The coefficients are not constants, so they're a function of t. So if you let this as or we know this solution, we let um, the full solution y equals vt y1t. So in that case, we will get y prime as v prime t y1t plus vt y1 prime t, and the second derivative as v double prime t y1t plus v prime t y1 prime t plus v prime t y1t plus v t y1 double prime t, and then substitute that to this expression. So for the first part, you have v double prime t y1t plus v prime t y1 prime t, which is the same with this next term. So we'll put 2 here, plus vt y1 double prime t. Okay, then plus pt y prime. Y prime is this, v prime t y1 vt y1 prime t plus qt times y is vt y1 t. Okay, now factor out, or we will group terms containing the same v uh, and derivative. So v double prime, for example. Okay, so yeah, for v double prime, we only have y1 t. Okay, plus, so for v prime, you have this 2 y1 prime plus, what else have v prime? This one, pt y1 t. And I guess that's it. Okay, finally, those with just vt. So plus terms with just vt, you have this one, y1 double prime t plus um, vt, that's this, so pt y1 prime t, and this qt y1 t times vt equals 0. Now take note, this is just our original differential equation. We're placing y by y1, but y1 is a solution, so this should be, or this should be 0. Okay, so you are left, or we are left with y1 t v double prime t plus 2y1 prime t plus p t y1 function of t, oops, vt equals 0. And this equation is actually first order. We have removed y double prime, so this is first order. We only have y, uh, first derivative of y1. Okay, we are then able to reduce the order, so that's why we have the term reduction of order of the derivative.